That was a really beautiful talk, and I think one thing that I'm always impressed by in hearing about the massive over-constraints that we have on things like the fundamental constants is that, in some sense, this constitutes amazing evidence that the overall structure of the physical theory you're applying has to be right, because you're getting all of these very different constraints that match up. And so I just wanted to ask about one thing. This is a really minor point in your talk, but you mentioned the lithium anomaly. And so I'm just curious, you mentioned that you had at one point thought that you might actually be able to explain the lithium abundance due to varying constants, but are there other options there, or?
Okay, so it's a huge debate, and our friend, and my colleague and friend, Elisabeth Vanjoni from the Institute, she's a specialist on that. So you have two options. So at least you have three options, I would say. Let's try to go to the first slide. Either you change the microphysics, and this is what we are doing here. We say, haha, these constants are not the same. Or you add new particles. For instance, we had a model in which we had a complete mirror world, like all the same model of particle physics, which is completely double, and you just allow for neutron and mirror neutron to oscillate from one world to the other world. So basically what you allow to do is to have a late time injection of neutron, and you can show that it changes the prediction of lithium. So this, as though you change the microphysics. It's very difficult because you don't want to affect the other abundances, and if you have decaying particles, for instance, well, it can screw up, later on process, and you are very constrained by that. The second possibility is that you have a problem with the observation of lithium, which I think is probably what people, Joe, you will confirm that. I mean, you are more specialist than I on this subject, but I think this is the main consensus between people working on this subject, that most probably it comes from the observation, the way we determine the primordial abundance of lithium. Okay, so this is the thing. The other thing is that you have to realize that what are we doing here? BBN is assuming that we have a homogeneous Friedman spacetime on the size of the observable universe, and we take this computation, and then we compare that to some observations which are in our local neighborhood today, which means that we are comparing computation which have been done here to something we have been here. So a third possibility would be that actually the universe is not completely homogeneous on that scale. Okay, so that was pointed by Chris Clarkson a couple of years ago. So again, I think, and I was saying that yesterday, we have the theoretical physics parameters, and we have the parameter from the cosmology. We are not even sure that the cosmological for the cosmology, they are the correct one to use. Right. And if this is the correct explanation, then, well, the standard cosmological parameters are not the correct parameters of the model. And there is a huge work today trying to see how well on the size of the observable universe this homogeneity and isotropy hypothesis hold. And I think there will be tremendous results, in particular during to CMB, because you see the CMB photons, they just go like that. So basically you just see the two spheres around us. But it has been realized that if you have some hot gas somewhere like in galaxy clusters, well, if you have light coming from here, it can interact with hot electrons here and rescatter to go to inside you. So basically, if you have a lot of such system, you are able to see the last scattering as seen from these different objects, and you are able to reconstruct up to the quadruple of the distribution of the temperature fluctuation inside our Hubble volume. So that would be very, if doing that will give you information not only on our past light cone, but inside our past light cone. And there are different ideas. With George, we propose to use the time drift of the redshift. So basically you would have on a 25 time scale, two light cones which are very close to each other, but it can kill a lot of models in which the universe is not homogeneous, for instance. And I think this is what is very neat with cosmology today, is that we are using the fact that these astronomers, they are doing incredible things in terms of the precision of what they can measure. And if we think hard, I think we can kill a lot of cosmological models. And I think this is a very nice, we have a lot of work still to think about how to use this observation to come with test of the cosmological principle.
I'm Cormac O'Rafferty from Ireland. I just wanted to touch on one, you very briefly mentioned the issue of motivation, and given that there's a philosophy aspect to this conference, it's something I've always wondered about. I mean, in comparison with the previous topic, eternal inflation, one can easily see the motivation there. I mean, inflation gives us very nice things, then we have this problem that we can't figure out how to switch it off, at least at a global scale, and so the price we pay is this business, to put it in a very simple way. In sort of tests of time-varying fundamental constants, if I can put it that way. It's more like we go looking for trouble. You know, that's what always amazes me about it. Is, you know, what is the primary motivation? Is it simply that we want to test whether our, let's say, general relativity, whether our theories are effective theories rather than fully, or is it more, are we testing, is it possible that, so, well, let me put it this way. Suppose one found a variation in a certain epoch in the fine structure constant. Would that then imply that perhaps the laws of physics were emergent? Could you say a little bit, in other words, are we testing whether they're effective, or are we testing whether they're emergent at a certain epoch?
Well, what I would, for sure, what I will know is that there is a new interaction somewhere. Most probably a scalar interaction, and there will be this kind of most probably long-range chemically dependent interaction, like a fifth force. So it will change the whole picture, because and George mentioned that people were trying to use the Higgs boson to do the inflaton. So that's the first thing. But now if we have this new interaction, it cannot be the Higgs boson because it's too heavy. So we know we have to go beyond general relativity. If you are going beyond general relativity, on these scales, all what you know from inflation has to be changed, because you have these new degrees of freedom and the dynamics will be changed. So I think it's very important. I mean, this was addressed in the previous talks. And as far as it works, you have to use the laws of physics, you know, and you extrapolate them boldly, but far outside of their domain of validity. And I think one of the things as physicists that we have to do and provide to people is the domain of validity and extend it. Okay, if I told you, well, general relativity is tested to 10 to the minus 3 in the solar system, this is fine, but you know, it's the solar system are curvature scale which are much higher to what we measure here today, I mean, which we have in the universe at low redshift, which means that, well, this acceleration of the universe may be a problem of general relativity at low curvature. This is a possibility. So, of course, you have these naturalness arguments, blah, 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 and you say numbers do not match, but this is based on all what you know in terms of physics. Is that if I ask a new interaction, a new particle, maybe even all these naturalness arguments may not hold anymore. So I think we have to be careful, and I think this is the goal of doing physics. See how well is this, you know, extrapolation working? How far is it working? And we have to provide that. And what I want to stress is that to provide this kind of information, it's a lot of work.
George Ellis, doesn't the Hoyle resonance depend on the fine structure constant? Yes. So can't you use that?
Oh yes, we did that. So thank you, George. So you know the whole argument about why do you get carbon? The argument is there by Hoyle, and it was used to predict actually the existence of a resonance in carbon. So here is the way it's working. So you want to do carbon, and in your star you just have, as we said from BBN, the first stars, they just have protons and helium, and there is a tiny lithium and beryllium, but you can neglect that. So what you want to do is to get from helium-4 to carbon. This is 4. You want to get 12, so you go through 8. So you want to do 4 plus 4 equal 8, and 8 plus 4 equal 12. So how do you do that? The point is that beryllium-8 is unstable. It has a lifetime of 10 to the minus 16. So you need the reaction rate to be sure such that basically during this lifetime you will be able to have an interaction. You will produce an excited atom of carbon, and it has to disexcite. But you see, you need this to be an efficient reaction, because you are at thermal equilibrium at a given temperature, and when you get this Q factor for this chemical reaction, if you change the value of this thing, it's exponentially dependent on the energy of this level. Okay, so the question is that now if I change the fundamental constant, this level can be higher, so I can increase the production rate of carbon. But if I start producing too much carbon, then of course I will produce oxygen and blah, blah, blah. I will produce more heavier elements. And if this is almost zero, then it will be frozen. I won't produce any carbon in my star. So how can you try to do that? So that was what we did a couple of years ago, so in 2009, with all this team, because to do that, it's a huge project. And what you need to do is amazing. So first, you have to start from your fundamental constant, and you need to compute all these quantities, so the binding energy of deuterium, the resonance energy of all these reactions in terms of this fundamental constant. And to do that, you have to use actually some phenomenological models, because you cannot solve the Schrödinger equation for carbon-12. So basically, this is what is called the cluster approximation, where you say, carbon is three-wave function of alpha particles, and you can solve that. Then you have these parameters. You want to have the reaction rate, which means you have to integrate over energy. It's a kind of, you can do it. It's a technical issue. And then you need numerical simulation of the star itself. So to get the stellar evolution. So you need people who know about stellar evolution, and then you will have a lot of parameters which enter the game, like mass of the star, initial metallicity, whether there is rotation, mass loss, and so on and so on. So this is a huge business. So we did that, and at the end, you produce the abundance of the nuclear element, and you see how the star evolves. So we did that. So you have this model. So this is the way the resonance energy depends on the intensity of the nuclear reaction. So with 0 is that this is standard physics. So there is a dependence in this nuclear, and you have a plus alpha, which depends on the Coulomb potential here. But you can show that the main effect is coming from the variation of the nuclear interaction. This is much more sensitive than the variation of alpha. So you do this computation. So this is the output of this model. So you have this Hamiltonian with this modified interaction, and you solve your Schrödinger equation, and you get these things. And then you put that in your code, and the first thing you get is this Hertzsprung-Russell diagram. So this is the luminosity as a function of the temperature of the star, the effective temperature of the star. This is the normal case. And you see, if you have a less efficient or more efficient 3 alpha reaction, you will change the way your star behaves. And in the end, you just ask, okay, what is the chemical composition of the star at the end of the core burning? And you have different two possibilities. So this is a standard way. In the standard way, you get some carbon and oxygen. This is what you get. So now if the nuclear reactions are more intense, you form a lot of carbon, but you don't have any oxygen. Okay? If this is if the nuclear interaction is weaker, you will produce your carbon, your oxygen, and then you will go to other nuclei like neon and magnesium. And basically, at the end, you will have a star with almost only magnesium in the core. No carbon, no oxygen, with magnesium star. So if tomorrow you come up and you observe a star and you can tell me this star, it has a magnesium core, or there is excess of, big excess of magnesium, that would be a way to put a constraint on such a variation of the fundamental constant. And if you want to say, basically, I want to have carbon over oxygen, which is of the order of 1, so I don't want to be much far, to be basically in this kind of interval, you see that you cannot vary the intensity of the nuclear interaction by more than 0.5%. This is real, numbers until just using what we know about this kind of nuclear physics. So the oil argument, I think, is a beautiful argument. But then if you want to put a number, like is it 1%, 5%, 0.5%, you need to go to all this nuclear physics, which is very difficult. And you need to have different people who knows about different fields of physics, because you know people doing stars and nuclear physics. So I was very glad when we got these things, because basically it tells you also that once you know this constraint, you can say that the binding energy of deuterium cannot vary by more than 0.1%, let's say, yeah, almost 1%. And that was very important because we had this possibility with BBN. So you see that if you take the two together, this is not consistent. So it's a way also to kill this kind of possibilities. So I think it's beautiful physics, it's standard physics, but you learn a lot about the way our world is, which I think people are worrying why is the world the way it is, but first we have to know how it is. So, so I think this is what we are trying to do in this more physical part of my life. So.
And we
thank you.
Jean-Philippe for his nice, beautiful talk.
Thank you.